Welcome to the Slide Rule Survival channel, where we talk about mechanical computations using a slide rule. For this lecture, what we're going to talk about is the logarithm scale and how it relates to operations on the slide rule and how the slide is laid out using a couple of the basic scales. So to start with, a logarithm is based on a thing called raising a number to a power. This is some base, that's the power, also called the exponent, and it provides some value on the right-hand side of the equal sign. When we talk about logarithms, two special things I want you to remember is a base raised to the 0 power will yield a 1 on the right-hand side of the equal sign. A base raised to the power 1 will yield the base on the right-hand side of the equal sign. So, for our case, if I raise 10 to the 0, I will get some value, and that value in this case will be 1. If I raise 10 to the first power, I will get 10 on this side of the equal sign. What I'm going to show you now are some numbers that I plotted, and these values here will represent some value on the right-hand side of the equal sign. So this top row represents some value, which is the right-hand side of the equal sign. This is the exponent that I'm raising for the base 10. So 10 raised to 0.3 approximately will give you some value, and that some value is 2. Similarly, 10 raised to the 0.78 power will give you some value, which in this case is 6, and so on. What I did was I simply said, okay, if I know what some number of interest is, we can work the problem in reverse, saying what is the log of the number 2? And the log of the number 2, if I had either a table or a calculator, would be 0.3. And in this case, I just wanted to point out I used a 2-digit approximation of a number using log base 10, or a table of common logarithms for our purposes. Now, if I had to plot out my number line, what you'll notice is that the spacing between each of these numbers is a little bit different. This is called logarithmic spacing, and it's not equal. So that's the thing that what we want to do is we want to get an understanding, an appreciation for what we just did. So notice that between 1 and 2, you have about 0.3 units of space. But if I look further down the number scale, 7 and 8, notice that all of a sudden I have 0.9 and 0.85, or about 0.05 units. So that's where I come up with the assertion that it's unequal in terms of values, and it's logarithmically spaced out. Now, what you're seeing here is what you would see projected or shown on a C scale or a D scale. What makes the logarithm a very, very powerful tool is two very special things. One, we have our ability to represent a very large, a very small number on a single scale. Try to imagine that I have some scientific phenomenon which can swing between, let's say, 1 and 1 million. Well, if I tried to do that with some sort of linear scale, you may not get a very good understanding of what behavior of the phenomena looks like. But if I'm using a logarithmic scale, we can change something that doesn't look very linear to something that is very linear. So in essence, now you can have a much cleaner relation plotted on a single scale. So in essence, logarithmic scale allows me to compress very, very large ranges into one single space. Second, we can take advantage of the slide rule and our logarithms to do basic calculations. Now, what do I mean when I talk about that? Well, what was discovered was that we can use the scales and logarithms to take complex operations like multiplication or division or taking the cube or square of a number, and now we can change them into much more fundamental types of computations that are much easier to do. To multiply two numbers together, we add their two logarithms, and I think we've touched on that on a previous video, and assuming that they are of the same base, and that's always going to be the case in the terms of using a slide rule, which represents log base 10 type of computation, except where noted. To divide two numbers, we subtract their two logarithms. So you can just see that in science, those two operations, which could be kind of a little bit painstaking, now are reduced to addition or subtraction. And that's a pretty powerful thing that you had in the days before you had a scientific calculator that fit on your desk. Now, let's say we needed to find the square root of a number. We divide its logarithm by 2. And what the asterisks are about is it depends upon how the scale is laid out. To find the square of a number, we multiply its logarithm by 2. And again, that depends upon how the scale is laid out. And different rules are going to use different types of scale layouts, depending upon the manufacturer. As always, your mileage may vary. It depends upon the rule that you've purchased and the way the guy laid the rule out when it was designed. To compute the square root, depending upon the number, what we're going to do is we're going to look at the number of digits we have in our number, even or odd. Laws 3 and 4 can be extended to cube roots or cubes by using the factor 3. We divide by 3 to get a cube root. You multiply by 3 to get a cube. If a k-scale is included on the rule, and typically on a scientific rule, you will have a k-scale. It's generally speaking something that's pretty common phenomena within science and engineering. Scale divisions. You'll have basically several types of divisions on a scale. They're called primary, secondary, and tertiary divisions. Large numerals on scales are typically going to be marked, and they're what we call primary divisions. Secondary divisions are tick marks between primary divisions. So you'll see numerals, and if you see tick marks, those are what we call secondary divisions. Now, what we're going to talk about next are going to be the case where you have situation in which on a 6-inch and a 10-inch rule, you're going to see 10 secondary division, and they are about 0.1 unit each. And between primary divisions 1 and 2, on a 10-inch rule, between 2 and 4, the smaller divisions will be 5 parts. For primary divisions 4, from 4 to the right index 1, spaces between the secondary divisions is 2 parts. For a 6-inch rule, the space between each secondary graduation from 2 to 5 is 5 parts. Up to 2, is 5 parts. In the middle of the rule, between primary divisions 2 and 5, spaces between the secondary gradations is 2 parts. From 5 to the right index 1, the smaller spaces aren't subdivided, and you are eyeballing the third digit on a 6-inch rule. For this reason, you can only get the first digits of a number with a reasonable precision on a 6-inch rule, and you can get or read about the first 4 digits of a number on a 10-inch rule. So to be clear, on a 6-inch rule, you might be able to get 3 digits. On a 10-inch rule, you might be able to get about 4 digits. Some observations. Now, what I want to do is I want to bring in a couple of scales to show you a few things that I think are important. I'm going to show you some text first, and then I'm going to pick up a scale and show you a few things I want you to look at. So what we're going to do is notice that an A or B scale has 2 cycles, meaning it goes from 1 to 1 at least twice. So I'm going to take my notes out of the way right now, and what I'm going to do is I'm going to put a scale in frame, and that scale will help us to show you some points, and I deliberately am going to show you both a 10-inch and I'm going to show you a 5-inch rule to show you that it's the same regardless of the manufacturer for a standard A scale. And again, this is used for square or square root. On this post slide rule, the third scale from the top is called the A scale. It corresponds to us doing operations with squaring things. Notice that what happens is we're going to go from 10 to the 0 all the way over to 10 to the 1. Then what's going to happen is we're going to go from 10 to the 1 all the way over to 10 to the 2. So in essence, we completed 2 cycles of our scale when we're doing a square using logarithm. Now what we're going to do is I'm going to take this out of the frame and I'm going to put into the frame a smaller rule. This is a smaller rule that has the A scale again, and notice what happens yet again. I'm just going to move that out of the way, the cursor out of the way to make my point. Notice how we go from 1 to 1, and now I'm going to move the cursor again. This has no significance or bearing on a calculation. I'm then going to go from 1 to 1 again. So again, we're doing 2 cycles of the scale. Now, for purposes of comparison, notice how it's half of that of the C or the D scale, which goes from 1 to 1 only once. 1 to 1 only once. So that is what we talk about when we're talking about using the scale, and that's why this is so powerful. An A or B scale has 2 cycles, meaning it goes from 1 to 1 twice, or as we just saw on our post slide rule, what it did was it went from 10 to the 0 to 10 to the 1, then from 10 to the 1 up to 10 to the 2. And as we proved on the smaller scale, and we could have done the same thing on the larger one, it has 1/2 the length of a C or a D scale, and this is why we use it with squares or square roots. Now, I'm going to make the same assertion with our K scale. It has a total of 3 cycles on it, meaning it goes from 1 to 1 3 times. Therefore, it is 1/3 the length of a C or a D scale. I'm going to take my notes off screen for a second, And what we're going to do is we're going to pull in our small rule again for ease of reading. And what you're going to notice is you'll notice that k goes from 1 to 1, from 1 to 1 again, and then I'm going to pull the cursor out of the way, and finally from 1 to 1 again. So therefore you can start to see a pattern that in my terms of raising things to a power, I have a lot of flexibility for what I can do with the slide rule, and I can compress a lot of numbers on the number line into a relatively small space. Typically, by the way, European rules are about 5 inches, American rules are about 6. So in a 5-inch space, I have 3 cycles of 10 running along that number line, just to give you some rough idea. So that is what we're going to show for the slide rules for now. Now I'm going to go back to my notes, and I'm going to go over to my next page of my presentation. So we're going to start with discussions now that we've kind of talked a little bit about spacing. We've shown you how you can have various numbers of cycles of the scale. We're going to talk a little bit about how logarithms apply to a slide rule. If you had 2 ordinary rulers that are linearly spaced apart, all you could do is add 2 numbers by adding corresponding lengths. So if I decided to add the number 2 to the number 4, I'd have to have a linear space of 2 units, linear space of 4 units. I align the 2 over the 0 here, so everything is offset by 2. And then if I look at 4, which is my other number I want to add, the result is 6. In this case, that's all I did, and that's all you can do. And that's the reason why a linear scale doesn't work well for us when we want to do more complicated operations with a much wider range of numbers represented on our number line. Now, here's the key thing. If I have scales such as C and D, and now they're spaced out logarithmically, we have the ability to add the lengths of their 2 logs together, and the product of the 2 numbers we set on the C and D scales can be read directly. And that's a very, very powerful thing. So now I don't have to worry about it. In essence, if you want to think about it, the slide rule is nothing more than a portable log table, as I will demonstrate shortly. So here's a small primitive graphic example. We align the left index of C over 2. We then take a look at our other number, 4, and we get our product, 8. So in essence, we add log base 10 of 2, log base 10 of 4, and the product is represented by log base 10 of 8. What we're going to do is we will now have ourselves a little bit of a proof. In science or math, generally what you'll find is there's more than one way to do the same thing. So what I'm about to show you is sort of say the old school way you could have done this if you didn't have a slide rule. So what I'm going to do is show you an old type of table called a table of common logarithms, that is to say base 10. And what I did was I looked up the 2 numbers and I added them together. And I'm going to show you how to read the scale, and we'll come back to the notes here in a moment. So I'm going to take the notes away, and now I'm going to show you 2 pages of our slide rule, and those 2 pages will show you what we're looking for. So the number of interest, the first number of interest, was the natural number 2. Don't worry about the 0 right now. Just focus on the fact that the first digit is the number 2. And there's nothing after that. So we're going to look down this column called the 0 column, the intersection of the 0 column with the row called 2 here yields this number 3010. So in essence, our target value in terms of a logarithm is 3010 from the natural number of 2. So what that means is 10 raised to some exponent, and we'll talk about what that exponent is going to yield the number 2. But in our case, we knew the number 2. We wanted to find out what this exponent was, and that's where we come up with the 3010. Now, what I told you before was 10 raised to the 1 power is equal to 10. So it goes to follow that this is not going to be 3010. It's actually going to be decimal 3010. Why? Because it's a number less than the number 10. So we'll keep that number in mind, and we'll show you in the notes how that works. So that's the first multiplication number of 2. That's our first factor. I can go to my second number, which is 4, which is right here. So the number of interest for us, or the factor I want, is 4. We have nothing after it, so its logarithm corresponds to 6021. And as we know, it's going to be decimal 6021. Why? Because of the fact that it's a number less than 10. So that's where that comes from. So that is what we're doing with that second number. So we have 6021, and we got that from the intersection of column 0 with that, and that yielded a number of 6021. So that's our second factor. Okay, let's go back to our notes just for a second, and we are going to come back to the next page of logarithms here in a minute, but I don't want to spoil the surprise. What we wrote down was we wrote down the number log base 10 of the natural number 2 is approximately equal to 0.301. We found from our table of common logarithms log base 10 of the natural number 4 is approximately equal to 0.602. And since I'm doing multiplication, I'm going to add this value of 0.301 to that value of 0.602. So m times n, these are simply two factors, is going to be log base 10 of m, log base 10 of n. So in this example, it's log of 2 plus log of 4, which is then 0.301 plus 0.602, and that yields a value, log base 10 of 0.903. So now you've got two ways that you could do this type of problem. One way is, again, we're going to use our log table is one way I can do it. So what I want to do is find out on a log table what value of 0.903 on a log table corresponds to some natural number. So in other words, 10 to the 0.93, and I'll just write it in, 10 to the 0.903 equals what? Right? That's essentially what this means. So what I'm going to do is I'm now going to put back in frame our second table of logarithms to show you that I'm going to look up this value on a table and see what it corresponds to. And you'll see it corresponds to a value of 8, but I want to prove it to you so you see it for yourself. I'm going to take this page off screen, and now what I'm going to do is I'm going to put my table of logarithms on screen. So I look down my table. I don't have any numbers after that, and here is 9031 right here. What does that correspond to? That corresponds, you're going to see a value of 8, right? And since I know I'm less than the number 10, this is going to be decimal 9031, 10 to the 9031, and that value is going to be 8 decimal 0 or 8. And we could also have used the calculator to do exactly the same thing. I'm not going to show you a calculator, but we use our definition. 10 to the x is equal to p, where x is called the exponent. In our case, x is 0.903. So 10 to the 9.3 is equal to approximately 8. I'm going to now go to my next page of my notes. In mathematics, you'll also often have a situation in which division is the inverse of multiplication, and many times in mathematics, one operation is the inverse of another, as we'll find out later as we get to upper level subjects. So the quotient of one number divided by another number is done by subtracting one number from another number. So let's take a look at our problem, and let's assume we wanted to divide 8 divided by 4, and we're going to get some value, which is 2, as you know from simple arithmetic. But since we're working off of a slide rule, in essence what the slide rule is really doing is log base 10 of 8 minus log base 10 of 4 is equal to log base 10 of 2. So what all this means is subtract this length from that length to yield our number. So what we're going to do is now we're going to go back and do everything opposite of what we did before. So we know from our table that the log of 8 is 0.903. We know from our table that the log of 4 base 10 is 0.602. If I subtract the 0.602 from the 0.903, and remember that represents the logarithm values of 8 and 4 respectively, we get 0.301. 10 to the 0.301 is approximately equal to 2 using either tables or a calculator. Number 8 is called the dividend, by the way, and the number 4 is called the divisor. The result is called the quotient. If we put our dividend on the D scale and our divisor on the C scale, we will develop what our quotient is if we look at it again. So using our table of logarithms one more time, just to prove to you what I've said, let's just review our basic problem. What we're going to do is we're going to start with our first page to get our first number, which is the number in the numerator or the top piece. And once again, I go to the number of interest, which is 8. I look down the first row and the intersection of the first row with the column, the first column of 0 with the first row of 8 yields 9031. So that's our first number. Now I have to go to my other page, which shows my second natural number, which is 4, which is right there. Once again, I go to this row, which is the 4, that column, which is the 0, the intersection of that column, 0, with that row 4 yields my second logarithm. Now I'm going to go back and I'm going to show you on paper what I just did. So that's how I just looked it up on the table. That now yields that number. And again, all I did was a simple subtraction. And that's 0.301. So now the question becomes, okay, if I know what that number is, that represents the logarithm to that base, which in this case is base 10, what logarithm corresponds to the value on the right-hand side of the equal sign? So what we will do is now we're going to go back one page, and what we will do is we will show it again. It turns out we look down, we look down, we look down. Seems to me that 0.3010 corresponds to the subtraction problem I just did. So this represents the logarithm. And now we read across to that column, and that tells me that the natural number is 2. And that basically is how we do that problem. So in essence, you can see that what this represents here is showing basically a table of logarithms, and in essence the C and the D scale on a slide rule basically replace this entire table here. That's basically what we just did. That's why a slide rule is so powerful, because whereas before I would have had to have carried a book and written lots of things down with paper and pencil, now I can do the settings directly from the rule. To give you a preview of coming attractions, what I'm going to do is I'm going to show you basically the addition of lengths. I'm going to add the length 2 to the length of 4. So this is, first of all, the length 2, 1 unit, 2 unit. So that's my offset. And my second length is 1, 2, 3, 4, which corresponds to a value of 8. Now, doing the problem in reverse, that is to say, doing its dual or its inverse, would be the problem of division. So I want to subtract 8 units from 4 units. So I take the value of the numerator divided by the value in the denominator, and now I go over and I look at the value here, and that yields the value 2. And essentially what I have just done is subtract 2 lengths. By having that number subtracted from that, I look at where my index lines up, and my index lines up there, and you know that that is correct. So you can now see how powerful a slide rule is, because I used whole numbers that were easy for you to understand, and anybody could check my work. But you can see that through the use of either the slide rule or the tables, I can develop the answer without using a calculator, by using some basic and simple math. This concludes this particular lecture. As always, I hope you've enjoyed it, and we'll see you again next time.